Okay, so let's continue. Our next speaker is Professor Solomon Vishkautsan. The
Okay.
title of the talk is Eigenvalues and Linear Recurrence Relations over Octonion Algebras. Let's welcome.
Okay, thank you very much. Hello, everybody. I'm very excited to speak for the first time in the Non-Associative Algebra seminar, and I thank the organizers for this opportunity. Um, so this is an overview of the lecture. I'm going to first recall what are Cayley-Dickson algebras quickly and polynomial rings over these algebras. And then I'm going to talk about eigenvalues left and right for Octonion 2 by 2 matrices. And finally, if time permits, I'm going to talk about linear recurrence relations of order 2 over these algebras. So parts of the talk are going to be joint, based on joint work with Adam Chapman from Tel Aviv Yafo Academic College and Ilan Levin from Bar-Ilan University. If there's any questions during the talk, then feel free to stop me. So let's start with the first part um, with the Cayley-Dickson algebras. So first I'm going to recall what is the Cayley-Dickson process or doubling. So we start with an algebra A, given algebra A with an involution. Which we denote by bar over field F. And we want to extend this algebra. We double its dimension over the field F. And we do this by taking A plus A L, where L is some symbol or generator. And so we denote this by B gamma, and we'll explain what gamma is in a second. So we choose some element gamma in F, and we define a product over this B in the following way. So we take Q plus RL times S plus TL. So this is sort of reminds you of the product of imaginary numbers or quaternion numbers. And we have this product TQ plus RS bar L for QRS T in A. And of course, this forces L squared to be gamma. Okay, and we extend our involution to B in the following way. So we say that Q plus RL bar equals Q bar minus RL. So here the bar is from A, and now we've defined the bar over B as well. Okay, and what is a Cayley-Dickson algebra? So at least one characteristic 2 is a characteristic of F is not 2, then we can start with F itself, and we take F with the identity, so it's not really an involution, but let's imagine it is. And then we take we do the Cayley-Dickson doubling over and over, and we get something like this. gamma 1, gamma 2, etc., where in each step we basically double the dimension of our algebra. And we have the following properties we can define for this algebra, which are the trace forms. So we have, for any element in the algebra, we define the trace to be q plus q bar, and the norm will be q times q bar. And both of these are maps from A to the base field F. And other properties of these algebras are that every element is quadratic over F. So we have this formula. It's the minimal polynomial is equal to 0. So every element is quadratic over the base field. And other things that are useful, we have this definition of the real part of an element is just q plus q bar over 2, and the imaginary part is q minus q bar over 2. So the most famous example of this is starting with the field of reals. And we have the following sequence. R going to C, the complex field, and then we have the quaternions and the octonions, and then the sedenions, where each time we choose basically gamma equals -1 here. And we double the dimension, as they said. So C is a two-dimensional algebra over the reals, and the quaternions, the real quaternions are four-dimensional, etc. And each time we do this process, we lose certain properties of the algebra. So R is an ordered field, and C is not. And H is already non-commutative, always alternative, but not associative. And the sedenions are, are not alternative, they're flexible, and they have 0 divisors. And we can continue this process, of course, ad infinitum. And these are basically just a recollection of what are Cayley-Dickson algebras and why they're important. And if there are no questions, I will move on to talk about the polynomial rings over this
May I
algebra.
ask you, what about the associative, this after octonions? Octonions are non-associative, but what about S? Does it have some property
Yes,
instead of
so the octonions are alternative, and the sedenions are flexible.
flexible?
So they retain, sorry, yes, AXA equals AXA. And it turns out that, I think it's a theorem by Hurwitz that says that all of the Cayley-Dickson algebras are flexible. So you don't lose flexibility when you go forward, but this is, I mean, this is as bad as it gets, let's say.
What about the next step?
So this is a 32-dimensional algebra, and it's still flexible.
I see.
I'm guessing not a lot of research has been done on this 32-dimensional one, but some research has been done on sedenions. And they have, the bad thing about them is that they have 0 divisors. Oh, and one final thing I wanted to say is that if our norm form is anisotropic, then elements have inverses. So we have sort of a kind of a division algebra structure where we have Q inverse equals Q bar over the norm Q. And so even the Sedenians have inverses, but it's you can argue if it's a division algebra or not because it has zero divisors. It's a bit of a weird structure. So now part 2 is polynomial rings. Over Cayley-Dickson algebras. So the first type of polynomial ring are standard or left. Polynomial rings. So we put all coefficients on the left. We could have put all the coefficients on the right as well, it doesn't matter. And our variable x, or variables if we have multivariate, so they act as central elements of the algebra. And we have the following structure. So our polynomial ring is basically just taking the algebra and tensoring it with the polynomial ring over the field. And so all polynomials just look like this. And the substitution map we have is P of lambda equals what we expect, AI lambda to the I. And it seems very natural, but it turns out that this substitution map is not a homomorphism, so it has a bit of strange properties, and it's very easy to make mistakes when working with them. Okay, and we say that two elements maybe I don't need this yet, so let me just say, okay, that we can define the conjugate of a polynomial. So we can define P bar of x equals okay, so we just conjugate the coefficients, and then we can define the companion polynomial, Cp of x to be Px P bar x, and it turns out that this is a polynomial with coefficients in the base field. Okay. And so we say that two elements in our algebra are quadratically equivalent. If two things happen, so if their norms are equal, and if their trace forms agree, which basically means that they're both roots of the minimal polynomial we talked about before, of the same minimal polynomial. And I will need in what follows the following result from Adam Chapman from 2020. So this works for up to quaternion Octonion Cayley-Dickson algebras. And they need also to be division algebras, which happens when the norm is anisotropic. And so every root of a polynomial, so I didn't define what a root was, but a root is exactly when we substitute lambda for in P, and then we get 0. So let me just write it down. So a root is when P of lambda equals 0. So every root of Px is a root of the companion polynomial. And every root of the companion polynomial is quadratically equivalent to a root of Px. And here, quadratically equivalent also means that they are conjugate. There exists some Q lambda, well, let's say like this. So they're also conjugate. And every root lambda of P satisfies the following property that we can decompose the polynomial from the right in the following way. So this is a generalization of, well, not generalization because there it's for general division algebras, but it's in the flavor of the theorem by Gordon and Motzkin from 1965, which states that the final part is true for division, associative division algebras. So this generalizes it also to the Octonion algebras. Okay. And so I'll just say for associative, this third part. Okay. So we have as an easy corollary, let's say from this that, so if we take the real Octonions, they are algebraically closed. For left polynomials. And what do I mean by that is that each left polynomial will have some root. And this is because we can take our companion polynomial, which is defined over the reals in this case, and it has some root, and it has to be conjugate to some, by the second part, it has to be conjugate to some root of Px, and then it means that there exists some root of Px. Okay. The second type of polynomial ring is general polynomials. So well, for an associative algebra, what we do is we take these monomials of the form A0x, A1x, xan, And this is a degree n monomial. But for a non-associative algebra, we need to basically take any two parts of this monomial and wrap them in parentheses. So we have quite a lot of different monomials for a non-associative algebra. So we need to add quite a lot of parentheses for the non-associative algebra. This is not a very formal discussion of these polynomials, but I hope you realize what I mean by all of this. So we need to add a lot of parentheses around, and that there's a lot of ways to add parentheses. Okay, and so what can we say about these general polynomials? So then we take a sum of these monomials, and this is called a general polynomial. Obviously, they're very hard to work with because of this mixed. So here x is not central, and we have a lot of freedom. So just as a quick example of this, so if we take, for example, f1 of x equals this polynomial, then it has, for example, infinitely many roots. We can take any real number and we get a 0 here. So this one has infinitely many roots. And this one will have no roots for this reason, because ix minus xi will never be real. So we have no hope even for being algebraically closed, but there are some conditions under which such polynomials have roots. So just as a remark, for left polynomials over the Sedenians, for example, it will already not be algebraically closed. So there are some left polynomials with no roots over the Sedenians. So there are classical theorems starting from the 50s. So Niven, Zhu, etc., that say that basically the quaternions and Octonion over the reals the general polynomials with a monic monomial leading term, the highest term. So if we have xn plus something, so we have a general polynomial. So this is the highest term. And if this is monic, and it's the only term that we have of degree n, then this polynomial will have a root. And the most recent result in this this vein is by Wilczynski from 2014. So these are started from the early 50s, so 1950 onwards. So Wilczynski generalized this by relaxing the demand that we have this monomial structure with monic, and basically he also says that if, for example, the highest term has only 1 0, which, for example, in this case, it happens when x is equal to 0, then this polynomial should have a root. Okay, so on the general polynomial, but we'll only need the classical result for this talk. Okay. So part 3, unless there's questions, is eigenvalues for Octonion algebras. So we have a matrix B over our Octonion algebra. So let me just give first the notation. So we have A some Octonion division algebra. And we take a square matrix with entries in this Octonion algebra. And we take a vector well, AN in this case is a vector space over the base field. And it also has a module structure over our algebra, the left and right module structures. And we are looking at 2 different types of eigenvalues. So we have left eigenvalues. So it happens when v equals lambda v for some lambda in A. And the right eigenvalue and generally, well, unlike the classical linear algebra over a field, the connection between the left and right eigenvalues is a bit mysterious. Over the quaternions, it's better understood, but over octonions, it's a bit mysterious at the moment. So what is known already? So not much. So Tevian Dre and others, they have a sequence of papers starting from the late 90s, so 1998 something, going forward to the early 2000s. They have a sequence of papers where they classify eigenvalues of Hermitian Octonion matrices. So 2 by 2 and 3 by 3 Hermitian Octonion matrices. And so they first classified the real eigenvalues, and then they generalized it, but I'm not even sure that for the 3 by 3, the general eigenvalue problem has not been solved completely. Okay, thank you, Adam, for answering the question that was in the chat. I missed it. So let's go forward and speak about 2 by 2 matrices, the general 2 by 2 matrices. And what can we say? So the idea for this result, so this is with Chapman. And this was from a paper that was published in the special issue. about left eigenvalues. So this is the first part of the eigenvalue talk, so left eigenvalues. So again, I'm talking about Octonion algebras, which are division algebras. And so we have some matrix A, B, C, D with entries from this algebra. And let's first take, it's a very simple kind of computation, but let's take an eigenvector which has a 0 in the first entry. And we're trying to solve this very simple equation. So obviously x should not be 0. And we get very simply bx equals 0, which implies that b equals 0. And the second equation is dx equals lambda x, which means that lambda is equal to d in this case. And of course, we can check that 0, 1, for example, is an eigenvector for the left eigenvalue d. And it's not hard to check that if b is equal to 0, which is what is implied from this situation, the spectrum or the set of left eigenvalues, which will be denoted by this, so this is the left spectrum, it will just be A and D. So, and the proof is very similar to how we would prove that an upper diagonal or lower diagonal, sorry, upper triangular matrix or lower triangular matrix, it has the spectrum equal to the diagonal. So the proof is very simple. So this is the first very trivial case. And now we discuss what happens if b is not 0. So we want to show that in some sense we can reduce the problem to the first entry being 1. So we sort of, it's not exactly a reduction to this case, but we'll see what I mean by this. So we want that our vector will be of this form 1 and x. Okay, so how do we do this? So we have our left eigenvalue. And what we can do, we can multiply on the left and right by some element z, okay, by some non-zero element z. And we get the following situation. So we know that our Octonion algebras are alternative, which means that they satisfy Mufang identities. And so let me just write it down. So they satisfy Mufang identities. And by this, we can check that this happens. So we can move the parentheses around using these identities. Okay, so how did this help us? So we can multiply v by some non-zero element. So we can we can basically multiply this element, the first entry by its inverse, and then we will get 1. And later we'll talk about how do we recover the original eigenvalue and eigenvector. Okay, but now we can start by assuming that our eigenvector has 1 in its first entry. Okay, so we have the following, again, a very simple equation, A, B, C, D, 1x equals lambda 1x. I want to solve it. So we get A plus bx equals lambda, and C plus dx equals lambda x. And then, very simply, we substitute lambda in the second equation, and we get C plus dx equals A plus bx x. And we get the following, basically, condition on x. So x has to be a root of the following polynomial. Okay, which is a left polynomial. And we also have a condition. So on lambda, I mean, we can recover lambda from the first equation here from x. Okay, so we find the root of this polynomial, and then we can recover our lambda. Okay, so we have this condition that lambda is a left eigenvalue. If we have b minus 1 lambda minus a is a root of f. So we already can say something about this. So if we're working over the real octonions, as we said, they are well, algebraically closed. It means there is some root. And so we proved the existence problem for left eigenvalue. So there always exists for a 2x2 matrix over the octonions, the real octonions, there always exists a left eigenvalue. So just quickly, so if b is equal to 0, then the diagonals are the eigenvalues and they exist. And if b is not 0, then we have some root of this polynomial and it induces some left eigenvalue. Okay. So how do we recover the general eigenvalue problem from this special case of this vector? So if we have an eigenvector with x not 0, so we can write it down in the following way. So we have t some invertible element. In this case, it's just x, and we can pull it out from the right. So we have the following situation where we have our one entry vector times t. And now we have S is a root of t minus 1 f of x. And we have to multiply back by t to get back to our original lambda. And then we get the following not very nice situation, but it's not so bad. But here the problem is that we cannot cancel t and t minus 1 because we don't have associativity. So this is the best that we can get, but it allows us to basically find all the left eigenvalues of a general matrix. So this is basically our solution for the left eigenvalue problem. Okay. As an example of when we use these two conditions that S is a root and this is the form of lambda, we can get a condition for 0 being an eigenvalue. And if d is equal to 0, then we have 0 if and only if c is equal to 0. And d is not, if d is not 0, then 0. So this is for b is not 0, I think. Otherwise, it's trivial that we have one of the diagonal entries should be 0. And we have the following condition. For 0 being in the spectrum. So there exists some t that satisfies this linear equation. Okay, so an example would be we can take I1, Ij, J. So this is a very strange example. So this matrix is invertible. Over the quaternions. So obviously 0 is not in the left spectrum over the quaternions of this matrix. But we can check that 0 is an eigenvalue over the octonions. And we can choose an eigenvector like this. Okay, so we have very strange behavior of this eigenvalues over the octonions. Okay. So the next part, the next section is about right Octonion eigenvalues. So this is from work in progress. We don't have a preprint yet with Chapman and Levin, and this is a small part of what we're working on. But we can show quite easily that there exist right eigenvalues, but we cannot yet recover all of the eigenvalues like we did in the left eigenvalue case. And let me give you just a very simple proof. This fact. So if we take an eigenvector of the form 1x, which here we are not justified in this choice, but it's a good first guess. It works. Then we get, and lambda here is on the right this time. So we have a plus bx equals lambda, and c plus dx equals x lambda. And again, we substitute lambda into the second equation. And we get c plus dx equals a plus bx, sorry, x times x plus bx, x times a plus bx. And this is equal xa plus xbx. And now we can, what we do is multiply by b on the left. So again, we need b to not be 0. So we multiply by b on the left. And we get the following situation. We have b. So we have bc plus b dx equals bxa plus bxbx. And here again, we can use alternativity. So any two elements in an alternative algebra generate an associative subalgebra. So this is by Artin's theorem. So we can move the parentheses around and we get basically here it is equal to bx or in other words bx squared. And then we can set y to be bx, and we get the following equation basically. Y squared equals b times b minus 1 y, a minus bd b minus 1 y minus bc equals 0. So what we have here is a general polynomial. And we have the leading term, the highest degree term here. It's unique. We have y squared, and it's monic. And this means basically that this polynomial must have a root over O. So in our preprint, we also prove that such polynomials have roots over any real Cayley-Dickson algebras. So any quadratic, general quadratic monic polynomial will have a root. So this basically, it was just for completeness to show that we know something about right eigenvalues, but not enough. Okay. Okay. So the final part I don't have a lot of time, but I will just go over it quickly. So linear recurrence relations over Octonion algebras. So I remind you that a linear recurrence is basically a recursive way to define a sequence. And so this is basically a general homogeneous linear recurrence over the Octonions. So we have alpha, beta in some Octonion division algebra. So given initial conditions, A0 and A1 in the sequence, then obviously there exists a unique sequence, AN solving this relation. The problem is finding the closed form for this sequence. So for the unique solution. So how do we go about this? So we start by using the methods from classical linear algebra. So we have the companion matrix. Of this linear recurrence is defined in the following way. And we have the following recurrence condition induced by this. So this is the recursive conditions, but well, basically the same linear recurrence, but just phrased as matrices. And if we repeat this, we can basically compute our linear recurrence using matrices, but it doesn't come out as nice as in the classical sense because of non-associativity. We have n times acting on A0 and A1. Okay, so here we have n times. So we would want this to be equal to A to the n, but it's not necessarily true. Okay, so how do we go about solving it? Just in a few words. So we notice that A is special. We only have two elements, alpha and beta, in the matrix. So they generate, or they live basically in a quaternion subalgebra. If we're in characteristic, let's say 0, we'll do the simple case here. So they live in some quaternion subalgebra of A. Okay. And we have the following lemma that we proved, that if you take A and V L, where A and V are, they live in this quaternion subalgebra, so let's call this Q. So A and V are in Q. So we can compute this product in the following way. L is the generator of the Octonion algebra. And we have the following way of pulling L out of this product. Okay. So now we can write our relation as follows. If we have A0, we write it as Q plus SL, and A1 is R plus TL. And I'll be done in just a second. I'm sorry for running overtime. And in this case, we can split it basically into two products. Each one of them is basically working over the quaternion. So we have associativity here, and now we have these powers of matrices. Okay, so basically now we want to compute these powers. And for this, we want to either diagonalize the matrices or go to a Jordan form. And over the quaternions, this can be done. We can compute the eigenvalues, and we can solve this completely. And in our paper, we have a preprint on the archive, which you can look at, and there's very explicit examples where we compute these linear recurrence relations all the way through by diagonalizing and coming to Jordan form for the quaternion algebras. So thank you very much.
Thank you very much for the very interesting talk. Are there any questions or comments?
Can I ask something?
Yes.
Could you explain the invertibility of this example, which you show in middle of the talk? It was matrix B, I think. This one, yes, this one, B.
Yeah. So this matrix has an inverse. Basically, you can compute it directly. And well, there's a determinant form and the way to compute an inverse over the quaternions. And you can check basically that this matrix has an inverse, a two-sided inverse. And obviously, because it's invertible, you won't have zero. So I wrote zero is, so this should be not. Zero is not in the spectrum because it's invertible. Okay,
I understand.
But it is an eigenvalue over the Octonions. Okay, because of this, you can check that this condition is satisfied, but you can also have, I mean, basically the explicit eigenvector.
Thank you.
Any other question? Okay, so if no other question, let's thank Solomon again. Thank you very much. Yeah.
Thank you.
Okay, so let's have a short break for 2 minutes. So let's come back in 2 minutes.